Okay, so implicit differentiation is just a way in which we can differentiate a function without having necessarily it written as y equal, as making y the subject. So things like x squared plus y squared, or we have multiple representations of y, we can differentiate each term with respect to x. So what we do when we've got a function in y, we're going to use a chain rule. So if I've got sort of some y function there, I want to work out the derivative of y with respect to y and then multiply by the derivative of y with respect to x. So I differentiate everything with respect to x, so I end up with the derivative of y cubed with respect to x, but knowing that y is in itself a function of x, I've got to differentiate it with respect to y initially. So process, differentiate every term now. So the derivative of x, so really what we're saying is the derivative of x cubed with respect to x is equal to the derivative of y squared with respect to x. So if I differentiate both sides with respect to x, so the left hand side is simply just 3x squared, and the right hand side will dy squared, the derivative of some function in terms of y with respect to x, is the chain rule. So the derivative of y squared with respect to y, which is just 2y, times the derivative of y with respect to x, which is dy dx. So every time we have a function in y, you're going to end up with a dy dx term. Okay, so now I rearrange that, and if I just come in here, I'll see dy dx is equal to 3x squared on 2y. Okay, so if we come across here to look at the calculator instruction where we implicitly differentiate, that the order in which we put the variables x and y is significant. So the first one there, comma x comma y, gives me 3x squared on 2y, which is what we got. The second one, comma y comma x, gives me the reciprocal of that dy, or dx on dy. So we've just got to be really clear. Dy dx is x comma y. So in some ways you want to almost write it the other way, because you want to say the derivative of x with respect to y. But really we're looking for the derivative of y with respect to x, but we have to put x comma y. Okay. So the second one here, now a little bit trickier. So the derivative of xy. So again, let's use a different colour. The derivative of xy with respect to x is equal to the derivative of 2x plus 1 with respect to x. So the right hand side, the derivative of 2x is simply just 2. Now the left hand side, we have a product of two functions. Yeah, y, don't forget, is a function of x, so we have a product of two functions. So the derivative, so u and v, the derivative of x is 1 times the second function plus the derivative of the second function, which is dy times dy dx, and dy is 1. So we end up with dy dx times the first function, which is x. So both of those expressions are my product rule. So that implies then I'm going to have y plus dy dx times x is equal to 2. So dy dx is equal to 2 minus y on x. Okay, which I don't know whether I've put that one in there. No, we don't seem to have. Okay, but that's okay. You can check that on a CAS yourselves. 23, we'll just keep working through nice and slowly. Change it up again. All right, again, find dy dx. Again, you could write, look, you could go y squared is equal to 1 minus x squared, y is equal to plus or minus 1 minus x squared to the power of a half, and then just work out dy dx. Yeah, absolutely. Very messy, and invariably in the questions, it's set up so that it is implied, strangely enough, for implicit differentiation, that the easiest way to come up with a solution is to implicitly differentiate. So again, differentiate every term with respect to x. D dx of x squared plus d dx of y squared equals the derivative of 1 with respect to x. So derivative of x squared with respect to x is 2x. The derivative of y squared is dy squared dy. So the derivative of the function with respect to y, which is just 2y, times dy dx. And the derivative of 1 with respect to x is 0. So that means we'll have 2y dy dx is equal to negative 2x. dy dx is equal to negative x on y, which hopefully over here somewhere is our implicit derivative using our imp diff function on the CAS to end up. All right. So then, I guess moving forward, there's nothing to say that you won't be asked to do exactly the same sorts of calculations that we get asked. Find the gradient of the tangent at a point, or find a tangent line or anything like that. So again, we've got a curve here. Find dy dx is equal to. So differentiate each term. So again, let's d dx of negative 2xy plus the derivative with respect to x of y squared plus the derivative with respect to x of 2x squared equals the derivative with respect to x of 5. Now, first term, we've got a product of terms. So again, in your head, the derivative of the first term, which is, so my functions are 2x and y, and the derivative of negative 2x is simply just negative 2, and the derivative of y is dy dy, which is 1 times dy dx. So that's v dashed. So I get the derivative of the first, which is negative 2 times the second, plus the derivative of the second, which is 1 times dy dx, times the first, which is negative 2x, plus the derivative of y squared with respect to x, so it's derivative of y squared with respect to y, which is 2y, times dy dx, plus the derivative of 2x squared with respect to x, which is 4x, equals the derivative of 5 with respect to x, which is 0. So we keep all the dy dx terms on the left-hand side and put everything else on the right-hand side. So I'll come over here. So I've got dy dx on the left-hand side. I'll take it as a common factor. I've got the second term there, which is going to give me a negative 2x plus 2y equals, take everything else onto the right-hand side. I've got a positive 2y and minus 4x. So then dy dx is equal to, maybe we'll take the 2 out the front, I get y minus 2x over, we'll take 2 out the front, and we'll get y minus x. So let's bring a negative sign for everything out the front to match it off to the CAS. A negative out the front will give me a 2x minus y. A negative out the front will give me an x minus y. And we get the same as our CAS. Okay, so that's what dy dx is equal to. Find the gradient of the tangent to the curve at the point 1, 3. So there's my x value, there's my y value. So dy dx is equal to, at the point 1, 3, so if x is equal to 1, I get 2 times 1 minus 3 over x was 1, y was 3, which is 2 minus 3, which is negative 1, over 1 minus 3, which is negative 2, which is a half, which again, obviously, if you look at the CAS there, we can do a lot of these things on the CAS. Substitute your values in on your CAS. Yeah. So look, I think it's just, there's a lot of product rule. We get that x squared y squared or x squared y or something like that, and you just got to make sure that every time you have a y present, you're going to end up with a dy dx expression. Okay.